Okay, again, just wait a few seconds until everyone's settled in, and we'll go right ahead and introduce the second talk of this afternoon session. And that's presented by Brian Kim from Stuyvesant High School in New York, and it's entitled Packing and Covering with Centrally Symmetric Disks.
Hello, my name is Brian Kim, and today I'm here to present my project, Packing and Covering with Centrally Symmetric Convex Disks. So the topic of packing and covering are two geometrical concepts, but they have frequent use in our daily lives. From the popular video game Tetris, where the player tries to pack falling shapes as efficiently as possible, to biology, where biologists try to pack DNA molecules so that as efficiently as they can. So before I move on, let me first define the two concepts for you. Given a family of shapes, a packing is an arrangement such that no two of them have a common point in their interiors. This is known as being mutually disjoint and is shown by the figures above. Notice that in the left we have a tighter packing than in the right, which is somewhat loose. For my project, I'm going to be looking at the tighter packing as they're more interesting. So an everyday example of packing would be trying to bake cookies. While baking, you're trying to arrange your circular treats in such a way such that they don't intersect, yet you're trying to maximize the number that you have in your tray, classifying it as a packing. So an analogous idea is covering. So given a family of shapes, a covering is an arrangement such that the union of all the shapes is the entire plane, as shown above, because every point in the plane is contained in one of these disks. An everyday example of covering this time would be trying to complete a jigsaw puzzle. So while completing a puzzle, you're trying to arrange these different shapes in such a way that you cover an entire surface, thus being a covering. So the topic of packing and covering have been studied extensively throughout history. As a matter of fact, 300 years ago, famous scientist Johann Kepler was trying to find the ideal packing arrangement for spheres. The problem stemmed naturally as soldiers from his time period were trying to find the best way to stack cannon balls. Kepler theorized that the best way to do this is the pyramidal configuration shown above, known as the face-centered cubic lattice, which corresponds to a density of around 74%. This was one of the most notorious problems in mathematics and has been only solved in the 1990s by mathematician Hales after the extensive use of computers and linear programming, showing that though the idea is somewhat easy to understand, it's very difficult to make progress on. So, however, my project doesn't deal with spheres or three-dimensional objects, but focuses on the planar case, such as disks and circles. So let me give you an introduction to packing and covering in the plane. So a contract requires a miser to make payment with a tray of identical gold coins, filling it as densely as possible. The contract stipulates the coins to be convex and centrally symmetric. What shape coin should the miser choose in order to part with as little gold as possible? So I know you guys all know some misers out there, or perhaps misers yourselves, so this probably might be relevant to you. So a bad idea for the miser is to pick squares, right? I mean, he's filling the entire tray with gold, so that's kind of, not so smart. So shapes that perfectly tile the plane are known as tessellations or tilings, and other examples include rectangles, parallelograms, or triangles. So what should the miser do? A fairly natural approach is the regular circle. So notice that no matter how you arrange these circles, there's bound to be some white space, which the miser is saving out on. So you can actually assign the number, the packing density, denoted by delta, as the portion of the plane that isn't covered by these gold coins. And we could find this by circumscribing a regular hexagon around each circle and then taking the ratio of the two areas, which is pi over 2 root 3, which corresponds to around 0.906. So at this time, you may be wondering, why are we choosing regular hexagons to circumscribe these disks? I mean, why don't we choose squares or rectangles? Isn't this somewhat arbitrary? Well, Toth proves a theorem which states that for each centrally symmetric convex disk K, we have that delta, the packing density, is equal to the area of that disk K divided by the area of H min, where H min is a hexagon of minimal area which contains that convex body. It's easy to see that H min has to be a hexagon that circumscribes the body. So the reason why this theorem works is that given any centrally symmetric hexagon, you could tile the plane perfectly, just like squares. You could think of a honeycomb structure, as we see it with circles, and then with this honeycomb structure, you can then place the disk inside each hexagon, which corresponds to a packing. And though the theorem is focused on centrally symmetric convex disks, this doesn't necessarily restrict it to shapes that are round or circular. As a matter of fact, going back to our problem, If the miser chose regular octagons, we could find H-min by extending the top and the left sides to meet at a point, and the bottom and the right sides to meet at another point, which forms H-min. We can then find delta by taking the ratio of the two areas, which is 12 minus 4 root 2 over 7, which is around 0.9061. Now, if you notice, this is actually better than the circle for the miser. We got 0.968, which is actually bigger than 0.9061. So the miser will be saving more money. So this begs the question, so what's the best shape for the miser? How could he save the most gold? I mean, don't you guys want to do that? So Reinhardt conjectured that the best tiling for the miser is something called the smooth octagon. And this octagon is formed by taking the regular octagon and then smoothing each vertex by imposing hyperbola on it. So then we could find H-min similarly, and then take the ratios to find delta, which is 0.902. This is substantially better than 0.906, as we saw for the regular octagon and the circle. I mean, this is just a conjecture. No one knows whether there is an actual worse shape out there. Tamila actually proved that the universal lower bound is 0.8926, but then there's no shape that corresponds to it yet. So out of all we know, the smooth octagon is the best. So at this time, I think you guys have a good idea of how packing works in the plane. So we'll move on to covering now, and we'll revisit our friend the miser as he looked at another problem. The same miser owns a cell phone company. The miser receives gold for all areas that have coverage and double the amount for areas with overlap. Each cell phone tower transmits waves in a shape that is both convex and centrally symmetric. What shape should the miser pick so that he receives the most gold? So now we know how the miser pays for his tray of gold coins. He uses a cell phone monopoly, and then, So at this time, we see an example of a covering above. It's a sort of elliptical figure, and it's not so bad for the miser. It's a covering, yet it has sufficient overlap. So the miser will be receiving a lot of extra gold. Yet again, the miser will not choose squares, because though it is a covering, there's no overlap. So there's no extra amount of gold being received. So how do we approach such a problem again? Would we use hexagons? Yeah, actually we do, because Toth proved an analogous theorem which states that for each centrally symmetric convex disk K, we have now the covering density denoted by theta is equal to the area of K divided by the area of H-min, where H-min is a hexagon of minimal area, and H-max, sorry. H-max is the hexagon of maximal area which is contained in that convex disk, and it has to be inscribed in it, as we can see. Theorem works for the same reason, because we could then tile these hexagons and then place the convex disk around each vertex, which corresponds to a covering. So going back to our problem, so what's the best shape for the miser? Well, if you chose circles, which is a fairly natural choice again, we could see that we could find the covering, the density, by inscribing a hexagon in it and then taking the ratio of the two areas, which is 2 pi over 3 root 3, which corresponds to around 1.209. It is actually the best case for the miser. This is the extremal case, and it was proved by the mathematician Sass that there's no better shape for the miser. Unlike with packing, the smooth octagon and the octagon were actually better, but then for covering, the circles is the best case. So I think you guys have a good idea of packing and covering in the plane now. So we'll move on to previous results and my main result. So my research project, like many others, rely on the work established by many previous mathematicians. As we saw in inequalities 1 and 2 above, those are the upper bound and the lower bound for the packing and covering densities, respectively. As we saw at 0.8926, there's no actual shape that corresponds to it. And for the covering density, 2 pi over 3 root 3, the circle actually satisfies it. Inequalities 3 and 4 are relationships between the packing and covering density, which have been studied to find a better idea of the two. In inequality 3, we have that the ratio between the covering and packing density is greater than or equal to 3/4. And then in particular, number 4 states that the arithmetic mean of the packing and covering density is less than 1, less than or equal to. My main results are given in the following. For each centrally symmetric convex disk K, we have that the product of the packing and covering densities is between 1 and 1.172559. So you may be wondering, why is this result significant? Well, by proving this inequality, we have a better idea of how shapes interact with each other to pack and cover the plane. Implicitly, my theorem proves that if a shape is good at packing, then it's also good at covering as well. And furthermore, it gives us a more efficient way of looking at shapes by deeming certain pairs of packing and covering densities as impossible. For example, a shape can't have a packing density of 0.9 with a covering density of 1.5, as their product is 1.35, which is greater than 1.172559. So if you graph the relationship between the packing and covering density in the plane, such that the x-axis is a covering density, packing density, and the y-axis is a covering density, then my inequalities correspond to regions in the plane which no shape can satisfy. So as we saw, the point 0.9, 1.5 is contained in my purple region, so there's no shape which satisfies it. And as we saw, packing and covering have extensive applications, such as cell phone towers with a miser, or packing, which can be used by manufacturers as they want to pack something as efficiently or as inefficiently as possible. So here are my acknowledgements. I'd like to thank my mentor, Professor Dan P. Ismailescu from Hofstra University, for his original inspiration and his patience with me. I'd like to thank the Siemens Foundation and the College Board for giving me this opportunity. And I'd like to thank George Washington University and their judges for hosting this wonderful event and their time. Thank you, and here are my references.